Hello everyone and welcome to our 12th class. We are still on chapter 5 on fundamentals of traffic flow and queuing theory. In the past few classes, we have been talking about traffic stream characteristics and important parameters that we use to define a traffic stream and how those parameters are related to. We also talked about a couple of distributions on vehicle arrival and also the distribution of headway between vehicles. And from this class, we start talking about queuing theory. So let's think for a few minutes about a queuing process. What happens when we have a queuing system? So if you think about it, you have customers, you have people that require a service, and the number of these customers is something that is generated over time. So maybe at one time interval you have 2 customers, next time interval you have 10, and this number could be uniform. Let's say every time interval you have 2 customers, or it could be varying from one time interval to the next one. What happens is that these customers are generated over time and then they enter a queuing system. So let's say these customers are generated and now they want to enter a queuing system, and a queuing system here could be, for example, a toll booth, it could be a bank teller or anything. So just these customers arrive and want to get a service, a certain type of service. So the person who provides service selects each of these customers one by one and provides that service. And that follows a discipline. For example, in most of queuing systems that we deal with, the discipline is first in, first out. So if you are the first person on the queue to receive a service, you are going to be the first person who's going to receive that service. But that's not always the case. There could be other disciplines that we will be talking about them. If you think about a recent example, that would be COVID-19 vaccination. That is not necessarily first in, first out. If you are the first person that wants to get the vaccine, but you don't belong to any of priority groups, you're not going to get the vaccine, right? So that's a different way of selecting customers to provide the service for them. And when that customer is selected, then the service is provided following a service mechanism. And when the service is done, the customer is going to leave the queuing system. So then you can think about the amount of time that the customer needs to wait to receive the service, and then there is another time from the beginning of the service up to the end, and the total time that the customer spends is going to be the summation of that time that's spent in waiting for receiving the service and the time that it takes for that service to be provided to the customer. So in the next slide, I summarize this a little bit more. So we have demand population or arrival pattern. This is the number of customers that is generated over time. You have queuing discipline. So it's either first in, first out, or last in, first out, or priority, or a different way of selecting customers. We have service mechanism or departure pattern. So this is, for instance, how long it takes to provide that service. So if the person that is providing the service is really familiar with what they need to do, your service time is going to be really short, right? And if they don't know, or if there is a lot of stochasticities involved, that service time could be long. And then we also have number of channels. So what is this? If you have one person providing the service, or if you have several people providing that service. So you can think about it when you are going to check out in a grocery store. So if you only have one checkout line open, number of departure channels is 1. And if you have 5 of those open, now you have 5 departure channels. So now let's focus a little bit more on the arrival pattern, okay? If you think about it, so far in this course, we have already talked about 2 different ways of arrival. One is equal time headways, the other one is exponentially distributed time headways. So equal time headways is when the headway between every 2 consecutive customers is identical to the same number. So what that means? What does that mean? It means that, for example, every 5 minutes a customer arrives. The second thing is what we talked about in the previous video, is exponentially or negative exponentially distributed time headway. So the headway between each 2 consecutive customers follows a negative exponential distribution, and it's not going to be the same number. It is a random number that changes over time. And based on this, we have different queuing systems. So if the arrival time between customers follows equal time headway, we have deterministic arrival. And usually we use a value of D to show that. And if you have exponentially distributed time headways, we have stochastic arrival. And we usually use M to show those systems. So now let's talk about queue disciplines. So we may have first in, first out. The first person in line would be the first person who's going to receive the service, and the first person who will be out of the system or out of the queue. Because when you get into receiving the service, if you have multiple channels, one server may take a little bit longer. So first in, first out, it means that the first person that is in queue is the first person that is selected to receive the service. We can have last in, first out. So the last person in queue is the first person who's going to receive the service. Can you think about a good example for a last in, first out or LIFO? Think about it. And I'm going to talk about examples later on in another slide. You can have service in random order. So you don't care when people have joined the queue to receive the service, but you look at people who are in the queue and you select one of them randomly to provide the service for. Can you think of a good example for service in random order? Think about that. And of course, you can have priority, and there are several examples for that I talk about, that I mentioned COVID-19 vaccination, which is based on priority. If you belong to group 1, 2, 3, or other groups, that is gonna determine when you're gonna receive the vaccine. Now, when your group is called and you are in, let's say, a vaccination site, then it is first in, first out. The first person that arrives there is going to get the vaccine first. But before that, there is a priority discipline that you need to be in a certain priority to receive the vaccine. So now let's focus on service mechanism or departure pattern. So service time, this is the time that is elapsed from start to finish of the service. So this is the duration of service. If you take your car to a car wash and there is a line there, the amount of time that you waited in line is not included here. The time from the moment that your car enters the car wash and the washing starts, the time starts from there and ends at the moment that your car is done and it's washed and it's about to leave the car wash. So this time could follow a distribution or could be fixed. Also, it could be different based on the customer that you have. If you have, let's say, a small passenger car, the wash time may be different than a large SUV. We can also have potential patterns, equal time headways based on uniform distribution, or you can have exponential distribution time headway. So this is the time that it takes to provide that service, and that time could be uniform or it could be stochastic and follow a exponential distribution. So if it's fixed, we use D. If it's stochastic, we use M. So the last component that I will be talking about is the number of servers or departure channels. We can have a single channel or server, so you have one server providing the service. We can have multiple channels or servers, and we can have infinite number of servers. We'll be talking about these two a lot or more in this course, and not much about infinite servers. So this is when there is no capacity on providing the service. So something like when you are connecting to internet, right? There is an infinite capacity to provide you with information that you want. But I want you to think about examples for the first two, and we will get to those in the next few slides. So I want to start with some examples that are not traffic related for single channel server. So think about what are some good examples that represent a single channel or single server queuing system. So an ATM machine, you have one server or a channel. A fast food drive-through that has like one channel is again a single channel queuing system. For multiple channels and one arrival channel, we can have a bank teller, so everyone enters the bank and then you have several tellers. Airport check-in, everyone enters the airport from one place and then you have several check-in counters. The last example is multiple channel or servers. This is when you are checking out and you are in a, let's say, grocery store. So you have people are arriving from different aisles and then they get to different checkouts. And so here you also have multiple servers, but also you have multiple arrival channels. So this is like exiting the grocery store. Examples of different queuing disciplines. So we have FIFO, LIFO, service in random order, and priority. And I want you to think for a few seconds about good examples outside of traffic for each of these. So let's focus on FIFO. So the first customer is the first one who is going to be served. So if you have a line in front of a bank teller, that is going to be first in, first out, right? How about last in, first out? Can you think about a good example for last in, first out? Elevator. So usually the last person that enters an elevator is the closest person to the door, especially when the elevator is full. So the first person to exit the elevator is going to be that person. So last person in is first person out. Or when you have trays in a cafeteria, so you see that they put trays or plates on top of each other, right? So we pick the one that is on the top, right? And that is the last one that is put there. So if you think about these trays as customers, the last one that arrives the queue is going to be the first one to be picked. And this plate or tray, this is the first one that arrived, right? And there is a good chance that this one never is picked up, because always when you have only a few plates left there, they're gonna put more plates there. So how about service in random order? Think about a good example of that. So it's like you have people in queue and you're gonna pick one of them randomly. So this is the case when maybe I ask a question and several of you in the class raise your hands, and then I just pick one person to answer the question randomly. So that's a good example of service in random order. How about priority? So COVID vaccination, COVID-19 vaccination is a good example, but can you think about any other example on priority? Well, if you have a sinking ship, we have priority. So we usually want to save children first. In hospital waiting rooms, the most injured person is going to be the first who is going to be receiving service. Or when you board an airplane, so first class goes first and then business class and so on. So there is a priority in boarding the plane. Now let's focus on some examples in traffic for FIFO, LIFO, and priority. So what is a good example of first in, first out in traffic? So if you have a traffic signal, the first vehicle that is in line behind the stop bar is going to be the first vehicle that is going to go through, especially if you have a single lane, right? So you have a condition like this. Here I have traffic signal, and here I have vehicles that are stopped. So this is the first vehicle in, and when the signal turns green, this is going to be the first vehicle that's going to be out. How about last in, first out? Can you think about a good example of last in, first out in traffic world? This is not that straightforward. So if you think about a queue departure behind a bus that makes a stop in a bus station. So if you have something like this, so you have really one lane to go and the bus stops here and vehicles want to go around the bus now. So if you have several vehicles that are stopped behind the bus, what is happening is that this vehicle doesn't get a lot of the first vehicle doesn't get a lot of opportunity to go. It's already stopped. And if you have several more vehicles that are stopped, it's not easy for them to go around. But if you have one vehicle that is approaching, you see a good opportunity for this vehicle to go around all of them. And when this vehicle is gone, then this last vehicle here can go, and then the next one, and then the one immediately behind the bus. I mean, to me, it not always happens this way, but it's a good example of last in, first out. And for priority, can you think about some examples? Well, if you have an intersection that provides service to different modes or classes of vehicles. So if you have emergency vehicles arriving, they get the top priority. Then if you have transit, they get the next priority. Now at some intersection, bikes and pets get the next priority, and cars the last, or these two could be swapped at different intersections. But definitely emergency vehicles get the top priority, and the signals change to allow them to go through, or even without signals changing, they're going to go through anyways, right? Then the signals are going to accommodate transit vehicles and then the other two types of users. Also, I want to talk about some examples on parallel or serial queuing systems. So can you think about good examples that you have parallel servers? Well, if you have a toll booth, several toll booths that you have, so let's say you have a freeway, and then at the end here you have several toll booths. These are parallel servers that provide service to vehicles that are arriving simultaneously. Retail store checkouts are also parallel servers. Some fast foods, you have several checkout lines, so you have parallel servers. For serial, so think about opening night of a movie. So you need to stand in several lines to get to the movie. First, ticket line. When you get your ticket, there is another line to get into the theater. If you want to get some snacks, there is another line. And when you want to get to the place that shows your specific movie, there is another line that you need to go through over there too. So you go through several lines, in not in parallel but sequentially. So just to summarize, we have several components for a queuing system. Now for traffic, specific to traffic, we always have arrival pattern, we have service or departure pattern, we have number of departure patterns, and we have queuing discipline. And when you have information on all of these four parameters, you have fully defined a queuing system, at least from traffic perspective. So if you remember, I mentioned that for arrivals, if you have deterministic arrival, we use D. If you have stochastic, we use M. For departure, same deal. If departure is deterministic, we use letter D. If it is stochastic, we use letter M. And then we also know the number of channels that we have by a number, 1, 2, 3, or something else that we have. So what we do is that with combination of these alphanumeric values, we can define a queue. So if I tell you I have something like D6, that means that my arrival is deterministic, my departure is deterministic, and I have 6 channels. The only thing that I have not talked about is the queuing discipline. First in, first out, last in, first out, or whatever. Now, for queuing discipline, our default is first in, first out, unless I tell you it is a different queuing discipline. But whenever we want to show a queuing system, we use something like this that I'm showing you. So I can have, let's say, DD1, DD2, DD whatever. I can have DM1, or I can have MM1, or any other combination of these. Okay? So what kind of statistics are we interested in knowing so that we can analyze a queuing system? We want to know average queue lengths. So this average queue length in traffic, it could be feet, how long is the queue, or could be number of customers. Average number in system. We want to know how many customers are in the system. Maximum queue length. What is the maximum number or length of a queue that we experience for this system? Average waiting time in queue. How long on average customers had to wait to receive the service? And lastly, average time in system. So this is summation of waiting in queue, oops, plus service time. So we would be interested in being able to find values for each of these statistics that I mentioned on this slide. Here is a perfect place to stop, and from the next class I start talking about DD1 queuing, and we will do so by going through a couple of examples, and we will learn how to analyze this queuing system by going through those examples. Have a good one.